All right, hello everybody. Welcome to 12.3, day 2. We left off talking about the dot product and how that kind of works. We also introduced the direction cosines and the direction angles. And so now we're going to pick up where we left off. And that was to decompose vectors into orthogonal components. Okay, and so generally the idea is going to be, you've already kind of been doing this, but we're going to elaborate as to what's really going on mathematically and why we're allowed to do certain things and assume certain things. And this will also help with understanding what a projection is when we get to that formula. Okay, so generally, let's say you have a vector v, and you want to decompose this vector into two vectors that are orthogonal to each other. Does not necessarily have to be horizontal and vertical. It can really be any direction. And so let's say E1 looks like this. Let's say E2, orthogonal to E1, looks something like that. Okay? And so now what we're trying to do is decompose V so that now it's along E1 for one of the components and then along or parallel to E2 for the other ones. Okay? And just for a reference, I'm going to call this vector here, or not vector, this angle between E1 and V, I'm going to call that theta, and this angle up here, I'm going to call that alpha. Okay, we'll refer to those in a little bit. Okay, so just based off of this picture, we know that I can write V as a sum of these two vectors that I drew. The problem is I don't know how long this vector is or what to call it. So right now what we're going to do is say, you know what? It's just going to be a multiple of E1. So I'm going to call that scalar factor K1. All right. And so that's going to be this first vector. The second one is just going to be a multiple of E2. So I'm going to call that scalar multiple, or that scalar factor K2. Okay, so we know that we can split up that vector as such. Okay. So now the question is going to become then, what is K1 and K2 exactly? Okay, so the claim here is that this scalar is just going to be the dot product of V with E1. In other words, when you're decomposing vectors, you can take the dot product of the given vector, and as long as these are unit vectors, which they are, okay, if I didn't make that clear enough, E1 and E2 are unit vectors. As long as you have unit vectors, you can just take the dot product of the original vector with the directional unit vector that you're choosing to use. Okay? What is going on here? Okay. Sorry, got a message on my screen and everything's good. Okay. So the claim anyway is that this scalar is going to be that, and we're going to go ahead and verify why that is. All right? And so what we could do is we're going to go ahead and use this definition and plug it right into there. And so now we get K1 E1 plus K2 E2 times vector V. Or I'm sorry, times vector E1. Okay, just plugging in for V here. So this is what I replaced. E1 is still there. And this is a dot product there. Sorry, got to make sure my notation's good to go. And now we can distribute that dot product as we discussed earlier. So now we get K1 E1 dotted with E1 plus K2 E2 dotted with E1. And so how does that help us? Well, we know that the dot product of a vector with itself is just going to be the magnitude of that vector squared. And we also know here we have a dot product of two vectors that happen to be orthogonal to each other by the setup that we have at the beginning. And anytime we have the dot product of orthogonal vectors, that dot product is going to be 0. Okay, so this term just disappears. Okay, and because we know the magnitude of E1 is just 1, we have now verified that K1 is exactly the dot product of the original vector dotted with the directional unit vector that we're using to decompose it. Okay, and then similarly, we can say that K2 is going to be V dotted with E2. Okay? And so what does that bring us to? Well, so now we can write, so therefore we can rewrite the original vector V. We're going to go ahead and replace K1 and K2 with what we've just established, and that's going to turn into V dotted with E1 times E1 plus V dotted with E2 times E2. And this portion here, so from here to here, and from here to here, this scalar, what used to be K1 and K2, okay, we need to make very clear that we know that this is the scalar component of V along E1. And similarly, this is the scalar component of V along E2. Okay, so just kind of clarifying what another interpretation for these values here. All right, and now kind of to bring things back to what you're probably used to seeing, we know that the dot product, so using some of the formulas that we've talked about in the previous days of notes, we know that the dot product of two vectors can be rewritten so that it's the magnitude of the two vectors multiplied together times the cosine between the two. So let's refer back to this picture. The cosine of the angle between E1 and V is going to be theta. Okay, and then that's still times E1. So I'm just rewriting the scalar in a different format. Plus, similarly here, we're going to have the magnitude of V times the magnitude of E2. And now, really what it's going to be, since E2 is technically this angle over here, the angle between the two when we're doing the cosine is going to be alpha. Okay? However, we also know from right angle trig that the cosine of alpha in a right triangle is just going to be equal to the sine of the other angle, right? So the cosine of alpha and the sine of theta are equal to each other. And so we're going to go ahead and, instead of saying cosine of alpha, which is what the definition for that dot product formula would be, we're going to go ahead and replace that with sine theta times E2. Okay, and this turns into what you're probably used to seeing and what you've been doing since last year. These magnitudes for E1 and E2, those are just equal to 1. All right, and so what we really get is just the magnitude of V times the cosine of theta times E1 plus the magnitude of V times the sine of theta times E2. Okay, is that still on the screen? Yeah, just barely. Okay. And so this is what you're used to doing, right? when you have a vector and you're splitting it up into vertical, or usually vertical and horizontal components, but really what we're saying here is any direction, right? You're just going to have the magnitude of the vector that you're splitting up and, times the cosine, and the magnitude times the sine, which is exactly what we've established here. Okay? All right. So, let's go ahead and do an example now. I'm going to set it up, and I recommend you pause the video, take a minute or two, try it, see what you can come up with, and then check your results. Okay, so let's let v equal the vector 4, 5. And in this case, you are being told what directions to use for the decomposition. And here are the unit vectors in those two directions. We'll go root 3 over 2, 1/2 for the first unit vectors components. And for the second one, we're going to go 1/2 negative root 3 over 2. Okay? Now, if you didn't have unit vectors, but you had just plain vectors, you're going to want to normalize these first so you can find out what the unit vectors are going to look like. All right. And so, yeah, let's go ahead and find the scalar and vector components of v along these two unit vectors that were given to you. Okay, and just to clarify here, here's the scalar components along E1, here's the scalar component along E2. This entire thing right here, this is the vector component. Same thing here, right? All right, so go ahead and pause the video, see if you can go ahead and find those answers, and let's check. Okay, so first, to find the first scalar component and to find the second one, you're just going to do v dotted with E1 and v dotted with E2. So we're just going to do those dot products. And so basically for the first one, it'll be 4 times root 3 over 2 plus, now you multiply the second components together, that's 5 times 1/2. Similarly with v dot E2, so you take 4 times 1/2 plus 5 times negative root 3 over 2. And we can simplify those. So you should get 2 root 3 plus 5 over 2 for the first scalar component. And for the second one, when you simplify, you get 2 minus 5 root 3 over 2. Okay, so those are the scalar components. This is the scalar component along E1, right here. And this is along E2. Okay, this whole thing. All right. Now, to find the vector components, you're basically just going to take those scalar values and now multiply it with the original vectors in those directions, which are E1 and E2. And so the vector components are going to be v dotted with E1, which we've already calculated, times E1. Same with the other direction. And so v dotted with E1 was 2 root 3 plus 5 over 2. And now that's going to get multiplied with the original E1 vector, which is root 3 over 2 and 1/2. And here we have 2 minus 5 root 3 over 2. And that's going to get multiplied with E2, which is 1/2 negative root 3 over 2. Okay? And if you want, you can certainly simplify those a bit. multiply this scalar times root 3 over 2. You're going to get 3 plus 5 root 3 over 4 for the first component. Now take the 1/2 times that value out there, and you're going to get root 3 plus 5 over 4. And now for the second one, you will get 1 minus 5 root 3 over 4, and now you will get negative root 3 plus 15 over 4. That's a negative root 3 plus 15 over 4. All right, so these are the scalar components. Now you take those scalars, multiply them with the original vectors, and these are the two vectors that we're talking about. Okay. Moving on. So now let's look at a quick example. Let's say we have a ramp. We have an object on this ramp. There's my object. Let's say we have it's 600 pounds. Rests on this ramp. Oh, it doesn't rest. It sits on the ramp, and it's attached to a rope. And so here we have a rope attached to it. Okay? And let's say this is a 30-degree incline. 30 degrees right there. The question is going to be, well, two of them. So how much force does the boat exert against the ramp? And secondly, in this scenario, assuming that the boat's not snapping off or the object is not sliding down that ramp, how much force is applied to the rope and by the way, the rope is parallel, right, to the ramp to prevent from sliding. Okay, so now this becomes really a problem like you've seen in the past. Okay, so let's talk about the setup here. Let me erase all this. All right, so let's kind of draw some vectors here. What do we have? We have a 600-pound force this way. So here's 600 pounds, right? And what we're trying to figure out is how much force is exerted against the ramp. Maybe I should put the 600 on the other side. So this is 600 pounds. And we want to figure out how much force is exerted against the ramp. So that's this blue one here. And we also want to figure out how much force needs to be applied in the direction of the rope, which is going to be parallel to the ramp. So that's really just going to be this. So here's my decomposition. You do a force at 90 degrees to the ramp, okay? And then the direction parallel to the rope is going to go that way. And so there's kind of the triangle that we're looking at. Okay? And so now let's label some things here. You know what? Maybe just to make it clearer, I'm going to draw this little triangle just a little larger. So we have blue, pink, and original. Oh, not too far. Sure. Okay. That's not much larger. Let me try that again. Blue. And pink. All right. So now, again, this is 600 pounds, okay, but interestingly enough, if this is a 30-degree angle and that's a 90-degree angle, then we're going to know that this angle up here is 60. So this is a 60-degree angle right here. Oh, sorry. This is 60. And so this, sorry, zoom in, right? That's going to be a 30-degree angle at the top. So this angle right here is 30. This is 90. That makes that 60. Okay? All right. So now we're going to know, here we have the 600 pounds on this side. Okay? And let's just call this pink one. Let's call this pink one F1. And let's call the blue one F2. Okay? Then we know F1, okay, that's a 60-degree angle between F1 and the weight, or the 600-pound force. And so that's going to be just 600 times the cosine of 60 degrees. Okay, and then F2, and that's for the magnitude. And now the magnitude of F2, 600 sine 60. Okay, and so that means we get, in one direction, we get 300 pounds, because the cosine of 60 is 1/2, right? This is 1/2. So 300 pounds, and this is on the rope. And the second one, 600 times the sine of 60. Sine of 60 is √3/2. So that'll be 300 √3 pounds exerted on the ramp. Okay, maybe I overcomplicated it a bit, but if you're already comfortable with this, this shouldn't be too bad. And if you are not, hopefully that makes sense. We split up the given vector, which is a 600-pound force, into the two directions that they're asking us about. The pink one is parallel to the rope. The blue one is the force exerted against the ramp. Magnify that triangle. This is still my 600 length. Doing some triangle calculations, you can figure out that that angle up here is 30, which means that this angle down here is 60. And so that's how we can split up those two forces. All right? Okay. So now, we're going to go ahead and try to finish up here with orthogonal projections, and then do a quick application of what we talked about. So that's the next piece, orthogonal projections. And we've actually already covered them. We just didn't call them that yet. But the vectors, the vector components, along E1 and E2 from before are also called orthogonal projections of V onto E1 and V onto E2, respectively. Okay? And the notation is going to look something like this. So the projection of V onto E1 is written abbreviated PROJ for projection, and the vector that is being projected or shadowed onto the other one kind of stays like that. And now you do a little subscript here so that you know which vector you're projecting onto. Okay? So it's the projection of V onto E1, and this one is written as the projection of V onto E2. Okay, so that's how you write the notation. And now we've already calculated these. And it's going to be helpful for us to come up with a nice, convenient formula to calculate these. So we already know, right, that that's going to be V dotted with E1 times E1. And this is simply going to be V dotted with E2 onto E2. Okay? So it's going to be the same formulas that we talked about for getting those vector components from before. It just also happens to be the case that when we talk about orthogonal projections, that's really the same exact thing. Okay? So now, generally, if we don't have unit vectors, so if we don't have unit vectors, okay, remember the first thing I think I mentioned in the previous example was that you need to normalize them. Okay, so let's go ahead and let's normalize it. So let's say we have the projection of V onto any old vector B, right? So using this formula here, we're just looking for one specific direction, but not two, okay? Then that's going to be the projection, that's the notation of V onto B. And now here's the formula for it, okay? So we know that it's going to be V dotted with this B needs to be converted into a unit vector. And to get it into a unit vector, right, you just take the magnitude of whatever B is and divide by it. So you're going to take B divided by the magnitude of B. And now you still have the original vector there on the outside. But again, we want to have it normalized to use that same calculation. So now it looks something like this. All right, now we'll clean it up a little bit and write it into a little bit more of a convenient calculation format. We can just take V dotted with B, okay, over, we got two magnitudes, so let's make it the magnitude of B squared, and then we still have B on the outside. So if you kind of regroup things and rewrite it, okay, this is the formula that you need to know for projection. The projection of V onto B, there it is. Okay, so now what does that look like? Let's draw a picture so we can really see what's going on and what we're calculating. So here's V, and let's say B is over here somewhere. Okay? So then what we're talking about, okay, you drop a perpendicular basically to where B is, and this portion, this vector there, okay, this would be the projection of V onto B. So from here to where that perpendicular, or the opposite side of that angle would meet B, that is the projection. Sometimes I like to call it, it's really the shadow of B onto, the shadow of V onto B, right? And so that's what's going on. Now, over here, okay, what is this? Right? Remember, this is an orthogonal component to the projection. Okay? And so, based off of this picture, if you arrange the projection so that it's pointing the opposite direction, something like that, okay, you can see that this side and this side are exactly the same vector, just different locations, but they're still the same vector. And so this up here is minus the projection of V onto B. And so that means that this blue vector here, you would just go V minus that. And that's how we would write it. So this orthogonal component is just V minus the projection of V. Okay? Now, our book, so again, actually clarifies this a little bit. So this is the vector component of V orthogonal to B. And the notation they use, okay, so this is how you would actually calculate it. You take the original vector, and after you found the projection, you just subtract the two. But the notation they're going to use is ORTH. Instead of projection, they use orthogonal. Okay? So it almost would be like the orthogonal projection of V onto B, but you don't have to make things overcomplicated. If you know these two vectors already, this is how you would calculate that. Okay? Let's see. Oh, and one more thing. The scalar value from the projection, which we had as V dot B over magnitude of B. Okay, so this value over here, the book calls that notation the vector component of V along B. Okay, so slightly different notation, but that's kind of what they're working with here. All right, so hopefully that makes some sense. A lot of different formulas at you here with this dot product stuff. Let's go ahead and do, let's see, how long is this thing? Oof, okay. Let's go ahead and do a quick example, and then we'll finish up with work. All right. So let's let V equal 3i minus 5j plus 2k, and B equal to 7i plus j minus 2k. And here's what we want to do. We want to find the projection of V onto B and the vector component of V orthogonal to B. Okay, so take a minute, pause it, try it, see if you can kind of navigate through those formulas we've just derived and come up with the answers. Okay, so first, to find the projection, we're going to use the formula for the projection of V onto B, which is just the dot product of V with B over the magnitude of B squared times B. Okay, and so if you calculate that dot product, V dotted with B, that's going to be 21 minus 5 minus 4 all over the magnitude of b. Well, that's going to be 49, 50, square that, you get 4, so 54 squared. The square root of 54 squared, and then that gets multiplied with b, which is 7, 1, negative 2. And so if we clean that up a little bit, let's see. We get 12 over 54. 12 over 54. This is really, sorry, I'm just working through the calculations. 12 over 54 is 2/9. So take 2/9 times that vector there, and you should get, okay, good, 14/9, 2/9, and negative 4/9. Okay, so that's the projection. And the second part, this part here, the vector component of V orthogonal to B, remember that that's just, so if this is V and this is B, we found this already. We found the projection, so that's this one. Now we're just finding this one here. Remember that the shortest way to do that is just take V minus this one, minus the projection, right? So that's just V minus the projection of V onto B. And so that's just going to be 14/9, 2/9, negative 4/9, minus, oh, skip a step. Forgot to write down V. V was 3, negative 5, 2, minus the projection, 14/9, 2/9, negative 4/9. And when you do that, you should get 27 minus 14, 13/9, and then negative 47/9, and 22/9. Okay? So, first answer, this is the projection, and this is the piece that's orthogonal to the projection. Okay? All right, I promise we're almost done. The last part is, again, something you've probably seen if you took Physics 1. We're just going to kind of tie it into what we've been doing here, and that's work. Okay, so hopefully you remember so the basic concept, let's say you have some object, right? And let's say we're moving, so this is point P. Let's say this is point Q. Let's say this gets moved all the way to so that this point P is now on Q. Okay? And let's say that we have a vector, a force, that's pulling it this way, exactly parallel to the ground. And let's call that just magnitude of F. Okay? So we have some force pushing or pulling so that we move from P to Q. Okay? And that's it. So you defined work last year, I hope, as simply the product of these two lengths, right? Force times distance. So take the magnitude of the force times this distance there, and then now you have the work, right? So, so again, keeping in mind, I think this is probably as simple as you guys did it last year, right? Force times distance is work. We're kind of clarifying all that stuff now and saying it's really the magnitude of the force vector times this length from P to Q. We're going to say vector PQ's length using that notation. All right. And now, interestingly enough, let's say, so we have, so let's say we have a different scenario. Let's say we have F kind of not parallel to the ground, right? So let's say F looks something like this. So then now what we can do is draw a triangle here. And really what we're interested in is the force in the direction of motion, right? Which is actually going to be the bottom part of this triangle. If we call this angle theta, okay, then we know, rather than F, the only thing that's going to affect the work being done is this portion here that's parallel to the ground. That's going to be the magnitude of F times the cosine of theta times the distance, which was the magnitude of vector from P to Q. Okay? So what is that? Well, if you pay attention to what's there, not necessarily the order, we got a nice little formula. We have the magnitude of one vector, the magnitude of another, the cosine of the angle between the two vectors. That sounds suspiciously like the dot product. Okay, so it's just the dot product of F with PQ. Okay? So this is a very nice, convenient way to calculate the work if you have the vectors given to you and you don't want to find angles or anything like that. You just take the dot product of the force vector, dot it with the direction vector, and you're good to go. Okay. Now, interestingly enough, we should mention here that this, right? This is also the same thing as the projection, just tying everything together that we've done this section, right? This is the projection of F onto PQ. And you can see that in the picture here, right? If this is P and this is Q, okay, then this portion is going to be the projection of that. Okay? All right. So last example, dealing with work. Let's say that we have a sliding door, and that sliding door gets pulled that away, and we're sliding this from P to Q, so from here to here. Let's say that this has a distance of 12 feet, and this force, a person pulls with a 50-pound force as shown. At 60 degrees, let's say this is 60 right here. Okay, at a 60-degree angle, with respect to the ground, to the floor. Now again, this is just in the interest of making an example. Why anyone would pull a sliding door this way, obviously no one would do that. You would pull parallel, right, to the ground. But just for the sake of an example here. So let's go ahead and find the work. The work here is going to be just the force vector times the distance vector, okay? Now we can change that up. Okay? So the force didn't label it. So this is 50 pounds long, right? We're going to have the vertical and horizontal components of that force. So I'm just following this formula there. This part will be 50 times the cosine of 60. This will be 50 times the sine of 60 degrees. And we're going to dot that with the distance vector from P to Q. Since we're moving 12 feet along the x direction, that x component's going to be 12. And there's no vertical movement there, so it's just going to be 12, 0. All right? And so calculate everything out. You get 50 times the cosine of 60, which is 1/2. This gets dotted with 12. And then you would add the two second components multiply together, which in this case is 0. And so we get an answer of, what is that, 300? 300, and we are in feet and pounds, so 300 foot-pounds of work. Okay? All right, so that wraps up today's lesson. I know there's a lot of content there, but you are now good to go with this section. See you next time.